Okay, so today we're going to follow this chain of reasoning about distributing energy at the microscopic level, and we're going to get to a definition of entropy and an actual definition of what temperature means and how to calculate it. We sort of left at the end of Monday's class with a question, which is, if everything's equally probable, why are we asking if some things are more probable than others? Which is kind of the key question. So we need to go back and talk about exactly what we meant there. So what is it that our fundamental assumption says are equally probable? Well, let's review some words we've been using. Remember that in order to talk about these things, although these ideas are more general than the model system we're using, we've been doing this in the context of a model of a solid. It's the ball spring model of a solid that we've been talking about for a long time, but we've added the additional assumption introduced by Albert Einstein to make this, that we could think of one atom in this ball spring lattice as mathematically being equivalent to three independent masses on springs, oscillators, one moving in the x direction, one y, one z. And if we have some object, so that's our model, ball spring model of the solid, except that we're talking about three oscillators for every atom. And we've been talking about dropping energy into these systems in little packets that we call quanta. Okay, so one quantum is the amount of energy, the energy difference, delta E, between two adjacent states for this quantum oscillator. So it's some number of joules, usually around a hundredth of an electron volt, which is about 1.6 times 10 to the minus 21 joules. And we've used the word microstate to talk about one way of arranging some number of quanta of energy among however many oscillators we've got. So last time we counted microstates. And so we said, well, if we had three oscillators, which is one atom, and we had one quantum of energy, then there were actually three possible ways we could put that one quantum of energy into our little one atom, three oscillator system. We could either put it in that one, or that one. So there are three possible microstates. So this is three microstates for one atom, three oscillators. And the fundamental assumption of statistical mechanics says that all these three microstates are equally possible, equally probable. So if we took our system of three oscillators and we took 1,000 pictures of them, then at different times we'd have a third of them would look like this, and a third would look like that, and a third would look like that. So these are microstates, one way of arranging however much energy we've got among the oscillators we have. What's a macrostate? Well, the macrostate is really the total amount of energy you've got in an object to arrange. So these three microstates correspond to a macrostate, which says that we have one quantum of energy in that system. So that's and so really some number of joules of energy to put into the system. That's the macro state. And there are three ways to arrange it, so those are the three possible microstates. So it says, our fundamental assumption says, given the specification of a macrostate, given the total amount of energy you've got, and the model of how many places you have to put it, any arrangement, and each of these microstates is equally probable. So that's important. And it's usually stated that the fundamental assumption of statistical mechanics, and we can say it in formal words or we can say it informally. The formal statement is that for any given macrostate, the total amount of energy you've got, every microstate that you can think of that's any way of arranging this energy among all the different places it can go is equally probable. We can just say, given the total amount of energy, we assume that each arrangement is equally probable. So then what are we talking about? What's the most probable arrangement? Yeah, we're really talking about what's the most probable macrostate given two interacting objects. So here's the simple example. The thing we're interested in is thermal equilibrium. And so if we have two objects, and they might start at different temperatures, like those problems we did when we were talking about internal energy, where you have this, 10 kilogram block of aluminum that starts out at 350 degrees Celsius, and you have this 5 kilogram block of aluminum that starts out at 100 degrees Celsius, and you put them together in an insulated container, and you wait. What happens? What's the situation when they finally come to equilibrium? So the question is, if we consider two objects that are going to come to equilibrium or that are in contact, and suppose we had a little object and a big object. So suppose these are nanoparticles. These are real solids. Nanotechnology is a big deal now. So these are nanoparticles, and suppose we had 30 atoms in this one and 100 atoms in that one. And suppose we had 10 electron volts of energy that we were going to add to this system. So what would you expect to see? Would you expect to see, you put it in and you wait, would you expect to see 10 electron volts in the small of energy above the ground state in the small one and 0 in the big one? Probably not, huh? So would you expect to see 5 eV of energy here and 5 eV here? Probably not. And so why not? Well, there are just a lot more places for the energy to go here. There's just a lot more atoms that can have energy. So we're interested in the little block should end up with less energy than the big block, you're thinking, because there's fewer atoms and fewer oscillators. And that turns out to be right. That's how it works. And so we're worried about when you have a situation like that where you've got two objects that have to share energy, what's the most probable partition of the energy, the most probable macro state that we could get. And the way we did this is by counting available macrostates and just saying, well, if there's more microstates available here, that's that's more likely. So here, the simplest system we took was something like two atoms in two quanta of energy. And so we had, and the question is, what do we expect? Do we expect 2 quanta here and 0 there? Or do we expect 1 and 1? Or do we expect 0 and 2? These are the possible macro states. So if we randomly reached into a bag that had lots of these 2 atom systems and we pulled one out, what would we be most likely to find? And the way we address that is actually by saying, well, we can make a table where we say Q1 is the number of quanta in object 1 and Q2 is the number in object 2. So we have atom 1 and the number of ways of arranging it, and Q2 and atom 2 and the number of ways of arranging that. So the possibilities here were 2, 1, and 0, and clearly that corresponded to 0, 1, and 2 here. And then we counted the number of ways we could do it. So this, if we were going to put 2 quanta in object 1, we had 2, 0, 0, and 0, 2, 0, and 0, 0, 2, and 1, 1, 0, and 1, 0, 1, and 0, 1, 1. So there turned out to be 6, we call this omega, the number of possible microstates, the number of possible ways of arranging these 2 quanta among these 3 oscillators. There were 6 of them. There was really only one way of arranging 0 quanta there, and so the total the total number of ways of total number of microstates corresponding to this macrostate was omega 1, omega 2, and that was 6 times 1, and that was 6. And if we did it here, we found that there was 1, 0, 0, and 0, 1, 0, and 0, 0, 1, so there were only 3. But there was the same thing here. So there were 3 of these, and 3 times 3 was 9. And here we're going to get 1 and 6, and 1 times 6 is 6. So this is really 21 different overall possible arrangements. So suppose I set up 21,000 systems just like that. Each of these systems has 2 atoms and 2 quanta of energy in it. And I lay them out in a big array. So I've got 21,000 2-atom systems, each in the same macro state. Two quanta. So each with 2 quanta. Let's not even say that. And I take a picture of all these systems, and that records what arrangement they've got. Then I'd expect on the average to see about 6,000 of them that have 2 quanta in atom 1 and none in atom 2. And I'd expect to see about 9,000 of them that have 1 and 1. And I'd expect to see about 6,000 of them that had 0 and 2. So that's what we mean by the most probable. There'd just be more of them in the picture in which the energy was shared equally. Now, what we're going to explore is what happens when these systems get a little bigger. 1 atom isn't really a lot. But so we mean what's the most probable state for these two objects to be in once they've equilibrated? That's the kind of probability we're talking about. And we had to assume that each of these arrangements was equally probable if you put two quanta into that one. So that's where the assumption goes. Okay? Well, I decided to set up 21,000 systems. Okay? And since 6 plus 9 plus 6 seems to add up to 21, then I figured that 6,000 of them would be, all right? So, I mean, we could do it on a percentage basis, too. It's the same thing. All right. The next thing I want to do is actually just be very concrete and talk about what this quantum thing would be for a real system. So what do we mean by one quantum? One packet of energy. So calculate that. Before I do that, I want to say that the quiz today is going to be on a topic that we've talked about Monday and today. And it's going to be a real basic thing, so if you have questions about basic things, you should be asking them now. Okay, so what do we mean by one quantum? Well, one quantum of energy is just this amount of energy that's required to take one of these oscillators from some lower energy state and put it up into the next higher energy state. So delta E is one quantum. And we remember from chapter 8 that this had the value of h bar times the square root of the angular frequency of the oscillator, K over m. In this case, since we're talking about a microscopic object, it was the interatomic spring stiffness and the mass of one atom, not the mass of a mole of atoms, because the oscillator is that. So let's do it very concretely for aluminum. For aluminum, if we measure Young's modulus by stretching an aluminum wire, and then we figure out how long an interatomic bond is, and how many interatomic bonds there are in a chain, and how many parallel chains there were, we get a number for the interatomic spring stiffness from Young's modulus of 16 newtons per meter. So however, we're thinking about our current model in a slightly different way. Because what we've done, remember, is we said, well, we're going to treat every atom in this lattice as if it consisted of 3 independent oscillators, meaning it's not connected to some other atom, it's actually connected to a wall. So we build a wall here, and now this atom isn't interacting with that atom. It's interacting with a wall. So each of these interatomic bonds, the spring length is really d over 2 in this model. It's like, it's not this whole length, we're only considering half a spring. And remember, when you cut a spring in half, the effective spring stiffness goes up or down? Up, because you have to apply more force to stretch it the same amount. So that would actually double the effective spring stiffness. And then furthermore, if you consider X oscillations, this atom is actually interacting with 2 springs here. So we have 2 half springs, and that's going to make acting in the same direction, so that's going to double the spring stiffness again. So we would actually say that the effective, in this model, the effective interatomic spring stiffness, thinking about it this different way, would actually be 16 times 4. It would be 64 newtons per meter. Not a big difference, but we might as well take the model seriously. So in this case, let us actually calculate the effective interatomic spring, the number of joules in one quantum of energy for aluminum. Okay, so when we talk about one quantum, if we're talking about blocks of aluminum, nanoparticles made of aluminum atoms, we want to know what this one quantum is, how much energy this actually is. Okay, and these are given in joules. It's a small number of joules, but okay. So that's correct. That's what it comes out to. And the important thing to note about this calculation is that these numbers are related, these symbols are related to the model. So this is the effective stiffness of this interatomic spring here. And what's attached to that interatomic spring? Is it an entire mole of atoms? No, it's just one atom, isn't it? So this is one atom, so we need the mass of one atom and the interatomic spring stiffness and multiply. Okay? So we're talking about an energy of, we decided that for aluminum it was 3.96 times 10 to the minus 21 joules. And what does that come out to in electron volts? An electron volt is 1.6 times 10 to the minus 19th. So it's going to be about something like 2 times 0.02 electron volts, something like that, right? Okay,